In this video, we're going to be looking at whether a function is even, odd, or neither, and the directions tell us to determine analytically, aka without a calculator, and then confirm graphically, and the fact that you should not be using a calculator is emphasized by the gray bubble on the problems, both on the study guide and in your textbook. Number 48, we have g of x equals x cubed. Now, before I start showing you how to do this, and I actually did examples in your study guide, but it might be harder to follow because lots of students tell me that this is confusing. So pay close attention, rewind this video, watch it 50 times if you need to, ask me 1,000 questions if you need to, but get this straight. This is the only way. And particularly when the instructions on a test item, which at some point you will see, say, prove that this function is even, odd, or neither, then you must do it this way or you will get no credit. So the way to do it analytically is always, 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 whatever you're trying to do, whether you think it's even, odd, or neither, here's how you find out. You plug in negative x. So you write g of negative x. And if you don't write that, you're already in trouble. Equals, and whatever you're plugging in, you're just going to replace x with. So on the other side, you're going to write in parentheses. Without the parentheses, it's wrong. Okay? So this is the first step of any analysis of whether a function is even, odd, or neither. Well, then you just do algebraically to the right what is legal. Okay? Well, this is where understanding your exponent properties or not is going to catch up with you. Okay? Because now we have this negative x being cubed. Well, here's what you have to think about. When I raise a negative number to an odd power, what do I get? I always get a negative. So then I can drop the parentheses and rewrite this as negative x cubed. Why? Because any negative number raised to an odd power is equal to the opposite of that same number being cubed, the opposite being a positive value. So what this says, because I started with x cubed, I ended with negative x cubed, and you don't need to circle these on your paper, I'm just showing you for emphasis here, then I know that I started with x cubed, ended with negative x cubed, means that I ended up with the opposite of my original function. So my answer should be, and it won't say this in the back of the book, but this is Twitty's expectation, therefore you must fulfill it. So your answer should be, since, or your conclusion, your answer is all part of this, the work is part of your answer in my opinion. Since, excuse me, g of negative x equals negative g of x, the function is odd. And you may write function as FCN throughout my class. And that's not my abbreviation, but some professors might insist that you write it out, but I will not. You have just proved that this function is odd. Okay, that is the analytic way to do it. Now, before we look at our graphical confirmation, you have to know what you're looking for in the graph. Well, remember, an odd function, since we've just determined this is odd, should have what I call odd symmetry, or not I call, that's not like my little thing, that's the whole math universe. So it should have odd symmetry, which means that whatever I see here should be mirrored here in the same way. Or it should match over in the other diagonal quadrants, if you want to think about it that way. So whatever's here should be mirrored here. So they should be reflective, but in a sort of a diagonal sort of way. So let's look at x cubed. And here it is. So as you see, as I was saying, in fact, let's go to a highlighter here. Notice how if I took this piece and then flipped it upside down, I would get this piece over here. So this is odd. And as I described in the study guide, and I will say to you over and over again, if you get this is called symmetry with respect to the origin is another way to describe it, but side-by-side quadrant reflection would be even, an even symmetry, and diagonal quadrant symmetry would be odd. Let's look at number 50. Same set of instructions. So we will go back to the same way we started the last one, and that is by plugging in negative x. So I just write g of negative x, then I write the right side with a negative x plugged in everywhere I see an x, and there's only one x in this, so that's really easy. And then I do the algebra that's legal. Well, the top stays 3 because there's nothing going on up there. Can't do anything with 1 because it's just sitting there too. All right, but now we get to the negative x squared term, and this is where all the action is. So we ask ourselves, what happens when we square a negative? If you're squaring the negative goes away. So I get back x squared. Well, once you've done all the algebra you can do, you compare what you ended with to what you started with. And in this particular case, you notice that they are the same. So your statement should be, since g of negative x equals g of x, the function is even. Again, we want to confirm graphically. So what we're already expecting is that this graph basically folds in half 2 reflections around the y-axis. It has to be symmetry with respect to the y-axis is what we call this. So notice you have 2 reflected halves, and that confirms your symmetry is even. All right, and then we have number 52. And if you've been paying attention, you already know what I'm about to write first, which is g of negative x. So then I copy exactly what I see, but I put negative x in parentheses in place of every x I see. So I have everything else exactly the same. And that was a parenthesis. And this is squared plus 3. There's no x, so that stays the same. So, I mean, I can't overemphasize the importance of this. Everywhere you saw an x, you should now see a negative x in parentheses. And there's the x squared that corresponds to the 1. Or, well, let me take the green off the square. And there's the x that I replaced from the first term with a negative x. So then, I just do the algebra that's legal. So, switching back to blue, we get, again, if I cube a negative number, it's the same thing as the negative of the cubed number. Notice the distinction there with the parentheses. Plus 0.04, and now I have to come back to this one. A negative x squared, if I square a negative, I get the same thing as if I squared the positive, so the negative becomes irrelevant, and 3 had no x to be changed. So now I compare what I ended up with, and let me make sure I did not screw that negative up so you don't see it. This was a negative x cubed, right? And then I got to compare that to what I started with in order to make my assessment. Well, what you notice here is that my first term is negative. The first term of what I started with was positive. So this one changed. So you can kind of come up with some sort of system. Now this may seem like overkill, but if you've got lots of terms or something, this will help keep you straight. All right, well then when I look at my second term and compare it to the term that I started with, it stayed the same. And anytime there's a constant, it's always going to stay the same because it didn't have an x involved to change it. So where on what number was it? Number 48, where there was only one term and it went from a positive term to a negative term, it became an opposite. On number 50, there was only one squared term and it stayed positive, so I got back the same function I started with. Here, it's neither one. So this is a neither, and that's how you know. If I don't get opposite or I don't get the same function starting, then it's neither. So our concluding statement is, and this is really where you get credit or not in a large way, although the statement itself is not enough, you have to have the work to support it. Since g of negative x does not equal g of x, and g of negative x does not equal negative g of x, the function is neither, and you can stop at neither, but if you're one of those people that it bothers to say something that doesn't feel like it ended, you could say is neither even nor odd. And that's the end of this video.